no question, then we are going to use this work energy theorem and also conservation of energy to solve problems involving the spring. Something like if you stretch the spring without friction, how much will be the kinetic energy, the final velocity of the block? With friction, how much is the final velocity of the block when you compress the spring a certain distance? So these are the things that we can calculate using work energy theorem and conservation of energy, right? So this time, our energy equation involves three things, right? Kinetic energy, gravitational potential energy, spring potential energy. So there are three factors there. Now, when the floor is not smooth, when it has friction, you have to add a further work done against friction there. So other than the distribution of energy, initial and final, when you have to distribute among these three factors, you also need to distribute some to the work done against friction, if there is friction. But the first two cases, no friction. Only the final one has friction. So you have to include the work done against friction. Okay, right. So you read this example 5.9, then I explain.
A block with mass of 5 kg is attached to a horizontal spring with spring constant K equal 4 times 10 to the power 2 Newton over m, as in figure 5.22. The surface the block rests upon is frictionless. If the block is pulled out of to xi equals 0.050 meter and released, A, find the speed of the block when it reaches the equilibrium point. B, find the speed when x equals 0.025 meter. And C, repeat part A if friction acts on the block with coefficient.
Okay, right. Now this xi is actually the initial position, right? The when I copy, they cannot change to the small subscript like that. Okay, this one I type, that's why I can change it to subscript. Xi means the initial position, right? I means initial. Xi means the initial position. X0, here, x equal to 0 means the equilibrium position. This is the natural length of the spring where no compression or stretching. It's the natural length. This is the equilibrium position. Right. So let me explain this problem. A block of mass 5 kg attached to a horizontal spring with spring constant 4 times 10 to the power of 2 Newton per meter. So there's a spring here and the spring constant is known. Okay, the surface of the block rests upon is frictionless. The block is pulled out to 0.05 meter and released. So it means like this. At first, it is like this, right? At first, it's like this. So as this block is attached to the spring, and at first the spring is in its equilibrium position. In its equilibrium position means the extension is zero. It is neither in a stretched or compressed. The extension is zero, the compression is also zero. So the displacement is zero. This is the natural length of the spring in its original state, neither stretched nor compressed. Okay, so this is it. So from this zero position, from this equilibrium position, we come like this. We come like this. Now what is this? From the equilibrium position, the block is pulled over a distance from this red mark here until this red mark here. The first red mark is 0 position. The second red mark is the xi. The xi is the position 0.05. So we call this position the initial position of the block. Okay, so the block is actually, the spring is actually in a stretched state. The spring is actually in a stretched state. Now, in this state, because it is not moving, the kinetic energy is 0. The gravitational potential energy is 0 because it's at the same level. It is not moving up or down. So the gravitational potential energy is 0. One thing is not 0. The potential energy of the spring is not 0. Why is it not 0? Because it has been stretched from 0 position to 0.05 meter position. So stretched. So the other two energy 0, only the spring energy is not 0. So this is what we have initially. And this is what we are going to substitute inside this energy equation. Inside this energy equation. Okay, so this, we call this the initial position, not this one. This one is the natural state of the spring. This is the initial, we have moved it to the right, and we call this the initial position of the spring. This one is the natural position. Okay, the initial position is like this. So now I'm going to release my hand, and the spring will pull the mass back. As this block travels to the left hand side, it passes through the equilibrium position where the extension is 0, right? Where the extension is 0. So they want us to find what is the velocity at this position. So when you release it, it moves through the center position, and how much is that velocity? Okay, so we call this position the final position of the block. So at this final position, the kinetic energy is definitely not 0. The gravitational potential energy is 0 because it is at the same horizontal level. So the gravitational potential energy is 0. The spring potential energy is also 0. Why is the spring potential energy 0? Because at this position, the spring is at its natural length. It is neither stretched nor compressed. So there is no potential energy at this position. Only at this position, no. Other positions, when the spring is either compressed or stretched, there will be potential energy. So only at this position, the equilibrium position, when the spring is at its natural length, neither stretched nor compressed, the potential energy is 0. Right. So we are going to compare these two states and equate that total energy. The total energy at the initial state and the total energy, we call this the final state. We equate the two energy because by conservation of energy, whether you are in which position, the total energy must always be the same. So using this energy equation, the total initial energy equal to the total final energy. So the initial energy, this one, we are referring to this one. The initial kinetic energy is 0 because you are holding the block, it is not moving. The initial gravitational potential energy is 0 because it's at 0 level. But the potential energy in the spring is not 0. It is half kx squared, not any x, but the xi, right? Xi. Then we come to the final position. Kinetic energy, half mv squared. Potential energy, 0. Final spring potential energy, also 0, because this is the equilibrium position. Okay, so we have already formed an equation involving the total energy. So just solve lah. Substitute in the values. K, the half and half can cancel away. K is 400. X is 0 0.05. 0.05. Then M is 5. V we don't know, so we call it V squared. So solving this equation for the value of V, you have to take square root, move the 5 over, then take square root. The velocity is 0.447. So, any question?
No questions, sir.
No question. So, one more time, we are comparing the energy at two different positions. We are comparing the energy at two different positions. Initial position, all the three energies, add them together. Final position, all the three energies, add them together. Conservation of energy, two of them the same. Make them the same, then solve. Okay, so this is what we are doing. Okay, right. Now, the second part.